I would like to motivate in a very simple way why there is a topological equivalence, a topological conjugacy between all unimodal maps. And the idea is very simple. Here is a one-dimensional unimodal map which has two branches. There is a monotone branch going up and a monotone branch going down. It has a critical value which maps into 1, which means that the left interval stretches over a whole unit interval, and the right interval stretches over a whole unit interval, but it flips. It has a negative slope. I'll refer to this kind of maps as a complete Ulam unimodal maps. The original Ulam map was a parabola whose critical value touched the ceiling of this unit square. But it's true for all maps of this type. So now, when you look at dependence of the value of x on x, you notice there are two fixed points. So there's a fixed point which is called 0, because we'll call this branch f0, and we'll call this branch f1. So there is this fixed point. If you start here, you will be there forever. So the symbol sequence of this branch is 0, 0, 0, 0 forever, the future symbol sequence. And then there is one fixed point which sits on diagonal in this plot. If I start on it, it'll return itself as a value, and it'll do this forever. So there will be two fixed points, 0, 0, 0, 1, 1, 1, 1. Each branch has a fixed point. What about periodic points? One way to understand periodic points is to look at the second iterate of the map. What happens with the second iterate of the map? This critical point, its value is 1, but value of the map at 1 is 0. That means that critical point in two iteration maps to 0. This fixed point stays where it is. This fixed point stays where it is because a fixed point of a map iterated once is same as fixed point map iterated twice, 3 times, etc. So these things don't move. But there is a value here which is the preimage of a critical point, in which in one iteration I end up at 1. So the value, this whole half interval here, stretches out and reaches the ceiling. What happens to this part? Well, this whole part maps onto that, and we know that one end is at 1 and the other one we already figured out is at 0. So there is a monotone branch going down. At this end, on a fixed point, it has a negative slope. So when we iterate it twice, we'll get a positive slope, so map will go up. We know that at this end, it's 0, and we know that its preimage is here, where it takes value 1. So this whole interval becomes stretched like this. This interval here will get stretched like that. And we find that the second iterate of a unimodal map is a map which has 2 segments going up and 2 segments going down. And notice that this is just qualitative. That is to say, it doesn't matter what this map is in detail. The only thing it has to do is it has to be monotonically increasing on one side and monotonically decreasing on the other side. So this will be equally true for something like unimodal tent map, or a parabola. Now look at the fixed point of this map. The two fixed points we inherited from before, so this is 0 repeated infinitely many times, also twice. 1 repeated infinitely many times, but there are new two fixed points. There's a fixed point here and fixed point there. What are these fixed points? If you look at the original map and try to understand what they are, you can see what they are. This is actually 2 cycles. you take a value of it, evaluate it, and then you flip it along the diagonal, producing diagram. It turns out this is something that at this moment is at 1, and it's 0 on the left-hand interval, and its future is 1. So this is periodic point repeated infinitely many times this way. Or on this side, it's first on the right side, and then one step in the future go to the left side. So here's a ternary 1, 0. So we'll get only 1, 2 cycle, which consists of 2 points. X, 0, 1 repeated forever, and X, 1, 0 repeated forever. And we can just read them off from here. So this is 0, 1 repeated forever. This is 1, 0 repeated forever. And now we can see that this unimodal map has a property, because it contains fixed point, that at least 2 steps in time, I see 1, 1. I stay on the right-hand side because I'm close to the fixed point. This one hops between here and there, so it can be labeled 1, 0, and its image can be labeled 0, 1. And this neighborhood can be labeled 0, 0, because in this neighborhood I stay around for 2 cycles. So now you can continue in the same way, and you find out that all complete unimodal maps, no matter what shape they have this structure that at every iterate, the number of branches doubles. So we went from 2 to 4, and now we go to 8. And the logic is just the same. This map, this first thing stretches until the pre-image here. Then there is a part which in one iteration maps here, and you find just 4 segments going up and 4 segments going down, and this is just a qualitative statement, so it's true for all unimodal maps. So now what will happen is this map will have a fixed point here and fixed point there, because 0 repeated 3 times is still fixed point, 1 repeated 3 times is fixed point. But now we will have 6 more fixed points in the third iterate of the map. And what are these guys? This branch of the map here has a property that I go 2 steps in time 0, 0. Here I went 3 steps in time and stay at 0. But here, after second step on the left-hand side, I jump there. So there'll be a point here, which we'll call 0, 0, 1. This branch will have a property that it's this whole interval originally were things that look like 0, 1 in the future. But then the left part will be called 0, 1, 1, and the right part will be called 0, 1, 0. And I'll actually work it out in different details. So here there'll be a point which will be called 0, 1, 1, and so on. So what will happen, and I'll work it out in detail, is there'll be 2, 3 cycles. There'll be a cycle that hangs out more on the left side. So it has 0, 0, 1 repeated forever. And there'll be one that is more of the time on the right side, of 0, 0, 1. And it'll consist of 3 points, x, 0, 0, 1. The next one, remember, it's a shift in the future, so this gets cyclically permuted by 1. And then there'll be 1, 0, 0. There'll be one of the cycles. And then there'll be 0, 1, 1. That will map into 1, 1, 0. And in one-time iteration by the shift, that becomes 1, 0, 1. So these are the 2, 3 cycles. Now, this picture gets very busy. So it's easier for me to illustrate what the cycles are by looking by drawing an original map as 3 cycles. Just easier to draw them. So I'll draw them here. So I have a unimodal map. It has 2 intervals, which I call M0 or M1. And now it has 2 fixed points, like any other general unimodal map. This one is again 0 repeated as much as we want, 1 repeated as often as we want. And now when I look at the preimages of critical point, there are 2 preimages. And what I do is I divide these intervals into 4 intervals, which are called M00. This hangs close to this guy. This one step in future I'm on the left, but then I jump on the right. Then there is an interval here that's called M11. And then there is an interval called 10. Now I'm interested in 3 cycles, so I have to go 1 level down. I have to divide this into 8 intervals. So what will happen is this interval will have 2 parts. I won't mark this one. That's owned by fixed point, but there will be a part which we label 0, 0, 1. And where else can we get 2 zeros? Well, here we'll get an interval called 0, 1, 0. This always has 2 ones, so that doesn't belong to 0, 1, 0 cycle. But this guy gets divided into 2 intervals. And the interesting interval is 1, 0, 0. The other one we call 1, 1, 1. And now I can actually draw this 3 cycles. And this is how you'll find it if you have symbolic dynamics and you're using Newton routine to find cycles. See, I know that it's in this interval, and that interval. Out of 8 possible intervals, there are 3 that have the right symbolic dynamics for this cycle. I will find a point which iterated once still ends up on the left-hand side, so it goes up here. So this point has a future 0, 0, 1. This one is on the left-hand side still, but then it'll get on the right-hand side. So it'll end up someplace here. And then I go to diagonal and find it. And here is my 3 cycle. This one is on the right-hand side, but its future is 0, 0. So you can see that if you understand how the things are ordered here, you can find all periodic orbits totally systematically just by looking where a certain symbol sequence maps under the shift in the spatial ordering, and then just connecting the dots and maybe using Newton routine or some other routine to make it exactly recurrent, not just interval by interval. Similarly, if I'm looking at the sequence 1, 1, then what I'll look at somebody. This gets divided into 2 intervals. There's one that's called 0, 1, 1. Then when I look how this interval is divided, there's a part that's owned by the fixed point. So that one has symbolic dynamics 1, 1, 1 3 times. And the other one looks like 1, 1, 0. And then I see how this is divided. There is an interval that's called 1, 0, 1. The other one that's close to this maps close to the fixed point, so has more zeros. So now again, I make a guess where the cycle is. It's someplace in here. So we find there are 2, 3 cycles, and the total number of fixed points is 8 because there are 2 fixed points of length 1 and 2 cycles of length 3, each one of them having periodic points. So the total sum is 3 plus 3 plus 1 is 8. Now, once we have this on any unimodal map, we have it on all unimodal maps. So, and the logic is just that iterates of a complete unimodal map are all complete unimodal maps. So topologically, they're all the same, even though there could be details of local curvature, etc. But as long as they're monotonely stretching or monotonely flipping, you're in good shape. So I'll just draw one of these cycles here. So for example, this point iterated once, lands here, then it lands there, and then it goes here. So this is point 0, 1, 1. This is point 1, 1, 0, and this is point 1, 0, 1. And I can draw the other 3 cycles.